Hello, dear students. In this section, we are learning the concept of nonlinear programming, that is one of the important forms of the problems that we challenge with them in the real world. And in the next slides, we review the different types of that problems and see how are them, what are the different characteristics of them, and we review some algorithms for solving them. As you see in this slide, the content that we review starts with an introduction about nonlinear programming, and then we review some important and some famous examples, just an overview of them and a sample application. And then we review this concept of graphical illustration of nonlinear programming problems, that this part it can be used for those nonlinear problems that have one or two variable and that can draw them in a graphical form. Inside it, we review types of nonlinear programming problem, one variable unconstrained optimization, multivariable unconstrained optimization. Then we review the model of KKT, the solution of KKT for a constraint optimization, quadratic programming, separable programming, convex programming, and non-convex programming. And we continue and we finish this chapter by our conclusions. As you remember, in our last semester, we learned the concept of linear programming, that was the fundamental role of linear programming in operation research is not inevitable, and the majority of the problems are based on this concept of linear programming. Just to review, I tell you that linear programming, the key assumption, the key concept in linear programming says all functions, as you remember, the functions were the objective function, and the constraint of that um, problem must be linear. Okay, all the functions should be linear. Although this assumption essentially holds for many practical problems, as I repeated before, in the majority of cases is valid, it frequently does not hold in some of them. Therefore, it often is necessary to deal directly with nonlinear programming problems. So we turn our attention to this important area. So as we see in our next two slides, we see that nonlinear programming problems are very different, that different algorithms are needed to use for different types of nonlinear functions. In this section, we review some of them in the next parts of this slide. In a general form of nonlinear programming problem, the objective is finding the vector of x that can be from x1 to xn. So the type of the form of this nonlinear programming problem for sure is similar to linear programming, that in a general form, in a standard form, is maximizing the function of x subject to 1 GIX less than or equal to BI. As you remember, in MQAG, in linear programming, we had this standard form, no maximization, and the form of the constraint less than or equal for those i's from 1 to m. And obviously, the constraint for variabilities says that the variability shouldn't be negative, should be non-negative variability. As you see here, is more than or equal to 0. So, as you see here in this problem, we have two important concepts, fx and gix, that are given functions of the indecision variables, okay, that we are searching. As I told you, I repeat, as you see here, this x that we have in bold is the vector of the decision variables based on the example and how many the variables that we need. We should find this bold x. Let's continue. Based on the types of fx and gix, okay, as you remember in the previous slide, we just learned that one mentions the objective function and the other one mentions the constraint of that problem, okay? So based on the type of them, we'll see in some examples we don't have any constraints, we just have the objective function. We name them unconstrained examples. In some of them, only objective function is nonlinear and constraints are linear, and the other one is vice versa. Okay, and based on these different types of fx and gix, there are different algorithms for the different types that I mentioned. So for certain types where the functions have simple forms, problem can be solved relatively efficiently. As we'll see, there are some small problems that we can solve them graphically, exactly like the linear programming that we had in previous semester and the graphical solution. But for some other types of examples and problems, solving even small problems is a real challenge. So it is important to know that there are different important types of nonlinear programming problems that we do not review here, and it's a very, very vast and big subject in operation research. The next following slides illustrate a few of many important types of problems to which nonlinear programming has been applied. The very first one is the product mix problem with price elasticity. As you remember, in the previous semester, in the last semester, we just focused on a prototype example in linear programming. As you remember, it was Windor Glasgow problem that in the next slides we'll review it. The goal was determine the optimal mix of production levels for a firm's product given limitations on the resources needed to produce those products, with the objective of maximization the total profit of the firm. However, all the options of that, I repeat, we'll review in the next slides, were linear, but in many product mix problems, certain factors introduce nonlinearities into the objective function. Okay, so here we want to focus on the concept of objective function, that how nonlinearity happens in it. Imagine a large manufacturer may encounter price elasticity, whereby the amount of a product that can be sold has an inverse relation to the price charged. In reality, guys, we see this item that if we buy something, for example, one item, it's 2 euros, for example, but the vendor says if you buy 3 of that, each of them is 1.5. Okay, so here is the concept that we are talking, that amount has an inverse relationship with price charged. We are just imagine this item. Thus, the price demand curve for a typical product might look like a descending curve that in our next slide we'll see what we are talking about. The firm's profit from producing all selling X units of the products then would be the sales revenue X Px. If we imagine Px is the price required in order to be able to sell X units. So the revenue, okay, the profit of the sorry, the profit of the firm is X, the number of the selling, multiplied by Px, the cost, okay, the price, sorry, of the product. So this one is the revenue xpx minus the cost of the that product. If we show the cost as C, so the profit of the company will be xpx minus C minus x multiplied by C. Okay, the revenue minus the cost of the problem. So let's check the next slide. To continue what we started in the previous slide, as you see here in the left-hand side is that relationship and that nonlinearity that we were talking about, that in the previous slide, that with the change of the demand, the amount of the number of the demand, the price will change this form, okay? And we just talked that the profit of the company, the firm, is a relationship of the number of production multiplied by the price minus the number of the production multiplied by the cost, the unit cost that we talked before. This is the nonlinearity that happens in our objective function. In the next slide, we review a short example that we'll see that this nonlinearity maybe is possible to happen in GIX. As you remember, GIX was the general definition of our constraint function, but in a similar form like the objective function. Let's review it. As I said in the previous slide, the concept of nonlinearity, maybe it's possible to happen in our constraint functions of our example. Okay, for example, if there is a budget constraint on total production cost, the cost function will be nonlinear if the marginal cost of production varies or just described. For constraints on the other kinds of resources, GIX will be nonlinear whenever the use of the corresponding resource is not strictly proportional to the production levels of the respective products. Another concept to clarify more this example is the reviewing the concept of the transportation problem with volume discount on shipping cost. As you remember, again, this concept of transportation was coming from our previous slide, previous semester, sorry. In that example, we were talking about transportation from and shipping goods from various sources to various destinations, given supply and demand constraints in order to minimize total shipping cost. Okay, it was the concept that we reviewed last semester as a linear function. Okay, it was assumed that the cost per unit shipped from a given source to a given destination is fixed. It means that for all of the sources and destinations, as you remember, demand and supply was fixed and was equal, regardless of the amount shipped. In actuality and in reality, this cost may not be fixed, okay? Obviously, there are marginal costs and they are different. Volume discounts sometimes are available for large shipments so that the marginal cost of shipping one more unit might follow a pattern that we'll see in our figure 13.3 that it's in our next slide. Okay, and the resulting cost of shipping X units then is given by a nonlinear function, obviously Cx, which is a piecewise linear function with slope equal to the marginal cost, like the one that we'll see in our figure 13.4. That there for the different for our different amounts of shipment, the marginal cost will be different. That is something like stairs that we'll see in our next slide. In this graph, exactly we are talking about what we had before. As you see in this figure, based on the amount shipped that is moving from 0.6 to 4.5, the cost decreases from 6.5 to 3. Okay, as you see here, if we ship the amount up to 0.6, the price will be 6.5. If it's from 0.6 to 1.5, it's 5, up to when it's moving and shipping from 2.5 to 4.5, the price is 3. So in a general form, we can say that if each combination of source and destination, if we name the source I and the destination as J, we can say that the cost of shipping xij unit, it means that the number of units shipped from source I to destination J is multiplied by Cij, the summation of all these shipments from destination I from 1 to M, source I1 to M and destination J1 to N will be the summation of these two Cij multiplied by Xij. I repeat, guys, at this moment we are just be familiar with the concept of nonlinearity, and here we see that what is the effect of marginal cost and nonlinearity on marginal cost. So obviously here you see again what our objective function changes. Okay, as you see here, there are different slopes for our problem, as you see here, guys. For example, from 0, the point 0, 0 to point 0.6 and 3.9, the slope is something, okay, that is 6.5. For the second part, this part from 0.63.9 to 1.5 and 8.4, the slope is other thing, and continuing this line, as you see here, it's just a form of showing it that how we say this one is a nonlinear form of example. In this part of this chapter, let's review the concept of graphical illustration of nonlinear programming problem. As you remember in the introduction, I told you, when a nonlinear programming problem has just one or two variables, it can be represented graphically. To this end, it is important to review a prototype example that we had in our last semester that helps us to understand better this concept of graphical solution and review some other concepts. Just remember this prototype example that was famous as the Winder Glass Company. The Winder Glass Company produces high-quality glass products, including windows and glass doors. It has three plants. Aluminum frames and hardware are made in plant 1, wood frames are made in plant 2, and glasses are produced in plant 3. And obviously the assembling happens in this plant. Because of declining earnings, top management has decided to revamp the company's product line. Unprofitable products are being discontinued, releasing production capacity to launch two new products having large sales, product 1 and product 2. So up to here, just to make a comparison, what we want to follow in this section, as you see here, when we have two products, okay, so it means that two variables, okay, they are knowing one or two. What is coming to our mind? Aha, maybe if it changes to nonlinear form, it's possible to solve. But at this moment, just follow the example and just review the linear problem that we had in last slide. Last semester. Oh my God. Let's continue. For these two products, product 1 and 2 that we reviewed in the previous slide, we just learned that we know here in this table that, for example, product 1 from plant 1 needs 1 unit, nothing from plant 2, and 3 from plant 3. Product 2 needs 0 from plant 1 and 2 from plant 2 and 2 from plant 3. And as we remember, this right-hand side shows the limitations of each of these constraints, okay? That if we name it as x1, this one, and the other one as x2, so x1 plus 0, x2 is less than or equal to 4. And we know in this type of problems, this is the maximization of the profit that 3000 x1 plus 5000 x2 should be maximized. Let's review the next slide to find some of our questions and doubts. So if I write my problem in a linear problem form, is exactly the translation of our table. My objective function is maximizing 3x1 plus 5x2 with the subject of x1 less than or equal to 4, 2x2 less than or equal to 12, 3x1 plus 2x2 less than or equal to 18. And we know our variabilities should be non-negative. Okay, this exactly comes from the slide of the last, the table of the last slide. Okay, so as you see here, just to imagine, guys, at this moment between parentheses, this is the general form and the standard form that we reviewed for our nonlinear problem as well. Okay, general form, I'm saying 1fx, a series of jxi, okay, and some non-negative variables. But at this moment, leave it here, come back again to linear program. In a graphical solution, because we have 1 and 2 variable, it is possible to draw it, okay, graphically. Easily, we have 3 constraints that shows us which will be our feasible region, that this is this gray surface that is our feasible region, and we know that this point that is 2 and 6 is our feasible result and the optimal result that we are searching. One important item in linear programming, we just learned that one of these corner feasible points, or corner point feasible, sorry, or CPF should be our objective, should be our optimal solution, okay? But in nonlinear programming, we'll see something contrary to this one. So now that when we refresh our mind, let's continue this same example with some changes in nonlinearity. Now, suppose the last slide, the last example of window glass company, the form of linear, but now we just assume that instead of second and third functional constraint, we replace this one as a constraint of this example. What happened? The objective function remained unchanged, z equal to 3x1 plus 5x2. The first objective function remained, the first constraint as well remained unchanged, x1 less than or equal to 4, but instead of the constraint 2 and 3, here we have another new constraint that is 9x1 square plus 5x2 square less than or equal to 216. So as you see here, now the form of problem from linear has changed to nonlinear problem. Okay, so as we'll see in our next slide, optimal solution now is not a corner point feasible solution, because we see this one has a form of curve that for sure there is no point, there is no corner point on it. So let's review our next slide. So as you see here, easily it is possible to draw this example graphically. Okay, the first constraint that says x1 less than or equal to 4, and this constraint that is 9x12 plus 5x22 less than or equal to 216. So with this constraint, we find our feasible region. The first difference between uh, linear programming and nonlinear programming is here. Although the optimal solution again is 2 and 6, but as you see here, it's not on a corner point feasible. It's not on a CPF out of our example. It's on this curve. It's not in a one feasible corner point in our feasible region. Now, let's review when the objective function changes to a nonlinear form. What happens? Now, in this part, we suppose that the linear constraints are kept unchanged, okay? But the objective function is made nonlinear, as we see in our next slide in a figure 13.6. Let's see what happens graphically to this solution. So as you see here, this is that familiar feasible region that we had in our last semester. But what has changed? Instead of having an objective function like 3x1 plus 5x2, we have this curvy, we have this nonlinear objective function for our example with the unchanged constraints. What happens here, guys? This is our objective function that gives us the maximum inside our feasible region. So let's wrap it up that again here we have the concept of feasible region, but like the previous part, you see necessarily the point of a maximum and the optimal solution is not located in one of our CPFs, corner point feasibles, one of these points. As you see here, or this point, as you see here, it's located here. That gives us Z equal to 857. The last change we do to see what happens to our example in this time, please assume that this one is our new objective function with the same constraints that we had before. So as you see here, guys, this point 3 and 3 gives us the maximum amount of Z, that is 198. As you see here, in comparison with this one, it's bigger than that one, okay? So what happens? Now we see in this nonlinear programming problem, our optimal solution, our optimal point is located inside our feasible region, okay? We just reviewed some items. Maybe it's curvy, maybe the objective function is something like a curve, and necessarily the point is not located in one CPF, and it can, but it's on our feasible region. In this example, we see that it's possible in linear programming, in nonlinear programming problem, the point locates inside the feasible region. So let's continue. Before entering to the types of nonlinear programming problems, let's review two concepts and learn two definitions that may be useful for our example. So when we are talking about nonlinearity, okay, we are talking about some phrases in our objective function or in our constraints with the form of a square or something more than that. So if I derivate 2 times of my variable, if it's less than or equal to 0, such a function that is always curving downward, or it's a negative form that we name it a concave function. A concave function, it's always downward, okay? Similarly, if less than or equal is replaced by greater than or equal here, the function is always curving upward, and it names as a convex function in our example. In next slides and next sections of this chapter, we review more detail of this part.